Welcome to Spectral Geometry in the Clouds. Today, it is our pleasure to listen to Nelia Charalambous, who's going to talk to us about the spectrum of the Laplacian on forms over open manifolds. So as usual, don't hesitate to ask questions if you want to. Nelia, the floor is yours.
Thank you, and thank you to the organizers for their very kind invitation to give a talk in this very nice seminar. Today, I'm going to talk to you about some joint work with Ricci on the spectrum of the Laplacian on forms over non-compact Riemannian manifolds, also known as open manifolds. So I'm going to begin with a brief overview on results about the form spectrum over non-compact manifolds. And I'm going to give you some of our results on the L2 spectrum of asymptotically flat manifolds, and also the spectrum when Ricci curvature is asymptotically non-negative. And I'm going to finish up with some recent work on the LP spectrum of negatively curved manifolds for forms, and with some couple of open problems for people to think about at the end if they're interested. So let me quickly remind everyone that over a Riemannian manifold, we have the Hodge Laplacian on K-forms, which is given by the exterior derivative d plus its adjoint in the Riemannian metric d star plus d star d. And this operator can be rewritten also as the Bochner or covariant Laplacian plus the curvature tensor on forms, on K-forms, which is also known as the Weizenbach tensor. This is WK that I wrote there. This is a self-adjoint and non-negative definite operator on L2 integrable K-forms. It can be extended to 1. And it can also be extended to the space of LP integrable K-forms. We'll talk later how one does that. And the spectrum of the Laplacian consists of the set of points in the complex plane where the Laplacian minus this point times the identity fails to be invertible on their respective domain where we're looking at. This definition is the same for any self-adjoint operator on a Hilbert space, but also for any closed operator on a Banach space. In general, if we're looking at a self-adjoint and non-negative operator like our Laplacian on L2, then the spectrum is always contained in the non-negative real line. And in general, we can break this spectrum into two disjoint sets. The first one is the essential spectrum, which are the eigenvalues of infinite multiplicity, or our cluster, also known as accumulation points in the spectrum. And the second set is the set of discrete isolated eigenvalues of finite multiplicity. In other words, the eigenvalues outside the continuous spectrum, outside the essential spectrum. Of course, we could also have embedded eigenvalues in the essential spectrum, but I'm breaking it up into these two disjoint sets for today. It's well known that if our manifold is compact, then the spectrum of the Laplacian on forms is a sequence, an infinite sequence of eigenvalues, which tends to infinity. And when our manifold is non-compact, then in general, we have both types of spectrum to appear. For the essential spectrum in particular, it's also well known that the essential spectrum of the Laplacian over the whole manifold coincides with the essential spectrum on the manifold minus any compact subset of the manifold. In other words, the essential spectrum gives us mostly information about what's going on at the ends of the manifold. At the same time, in the non-compact case, I'm going to make the argument that the spectrum strongly depends on the geometry of the manifold by giving you two very well-known examples. The first one is the Euclidean space, which has zero curvature and polynomial volume growth. And it's well known there that the spectrum of the Laplacian on K-forms is maximal, as large as it could be on L2. It's the whole interval from 0 to infinity. Of course, there are no L2 integrable eigenfunctions or eigenforms in Euclidean space, but we have what's known as a large class of approximate eigenfunctions. Okay. And one can go about building those, for example, in the case of functions, by noting that the Laplacian is essentially the second derivative in the distance function away from a point. and then building approximate eigenfunctions of the point of the type a sine or cosine into this I now, square root of lambda, where lambda will be our desired eigenvalue, times an appropriate cutoff function. So one can show that we can have a sequence of these approximate eigenfunctions such that the Laplacian minus lambda at this function can tend to 0, okay, in the L2 mode. And the way you can build, and you can do this for any lambda which is greater than or equal to 0. For K-forms, your approximate eigenforms will look like these functions times the harmonic form, which is given by the, for example, by the wedge product of dx1 up to dxk. Okay, so this is a flat non-compact manifold. At the same time, we have a diffeomorphic space, the hyperbolic space of n dimensions, which has constant negative curvature and now exponential volume growth. Okay, so a different metric on it. And it was proved by Donnelly that on this manifold, the L2 spectrum of the Laplacian on forms is now a connected set for k less than or equal to n over 2. And it's given by the interval that I wrote there, which depends on both the dimension n and the order of the forms k. So its first point depends both on the order of the forms and the dimension of the manifold. And in particular, when k is n over 2 in even dimension, it also has a gap, because 0 will now be an eigenvalue of infinite multiplicity for n over 2 forms. Also note that for n minus 1 over 2, the first point is 0, right? And up to half dimension, this interval gets larger and larger. It's the maximum. It can be in like, well, and essentially the maximum has a jump in half dimension depending on n. And then it shrinks again as k goes all the way. In this case, I'm giving you a short description of how one can also build the approximate eigenforms. You can look at, if you're working in the upper half plane model and y is your positive variable, you can look at powers of y. These are all now exact eigenfunctions that are not L2 integrable. I wrote their respective eigenvalue there. For the appropriate cutoff functions, you can build now your eigenforms for any dimension and prove that all of those points that I wrote are indeed going to be in the spectrum. Also in 1990, Matteo and Phillips, they proved that if we now have any geometrically finite hyperbolic manifold, in other words, a quotient of hyperbolic space whose fundamental domain has a finite number of sides, then the spectrum of the Laplacian on K-forms is the same as the essential spectrum of the Laplacian on K-forms is the same as the spectrum of the Laplacian on K-forms over hyperbolic space. I have the same interval. And in the case of infinite volume, again, I also have to add 0. But in this case, we could also have a discrete spectrum. We could also have some isolated eigenvalues of finite multiplicity. Another interesting important result is McKean's estimate that tells us that if we have now a simply connected n-dimensional manifold whose sectional curvature is bounded above by a negative constant, then we'll know that the bottom of the function spectrum will start at a positive number or will be greater than or equal than a positive number, the one that I wrote there, depending on the bound on the sectional curvature. And we can get a similar result for K-forms, but there we would have to sort of subtract the lower bound of the Weizenbach tensor, of the curvature tensor on K-form. So we see that in negative curvature, the form spectrum or the function spectrum doesn't have to start at 0. There are also many examples of manifolds whose function and form essential spectrum can have an arbitrary number of gaps. In other words, the spectrum is not discrete, and we can have the spectrum consisting of an infinite number of intervals. There were various results in this, various examples of manifolds that were constructed by Lott, Post, Shen and Tran, and also Leal and my co-author Lu, for functions, but also for forms by Anne, Garon, and Post, and also Leal and Zhu. But a common characteristic of these spaces is the fact that they are all spaces that have negative curvature. And they are mostly periodic manifolds or coverings of manifolds. In other words, the existence of gaps in the essential spectrum seems to be a characteristic of negative curvature. There are no known examples of manifolds with that are asymptotically flat, for example, that have gaps in their spectrum, in their essential spectrum. For functions, it is there are large classes of manifolds now which have maximal spectrum, which has spectrum 0 to infinity. It's well known that if we have any flat manifold like Euclidean space, the spectrum on functions is maximal. And it's also been proved in a fairly general case that the spectrum of the Laplacian on functions is maximal if the Ricci curvature is asymptotically non-negative just in the radial direction away from a point, under the additional assumption that if the volume is finite, then the volume does not decay exponentially at x0. So the volume of these manifolds grows sub-exponentially at x0, but it doesn't have to grow uniformly sub-exponentially. And this is the main difference with all previous results that I'll also state in a little bit. The proof of this result relies on a generalized Weyl criterion that allows us to find a more general class of approximate test functions to prove that lambda is in the spectrum. And what it tells us is that instead of looking at eigen functions such that the Laplacian minus lambda on this eigenfunction goes to 0 in the L2 norm, it's enough to find a large sequence of bounded now test functions with uniform norm 1, such that the Laplacian minus lambda on these test functions goes to 0 in L1. Okay, so they are an L1 it's an L1 intersection L infinity criterion, in other words, showing us that lambda will be in the middle in the L2 spectrum.
We have a question from the chat.
Yes, I'm sorry.
Chris Judge asks whether the essential spectrum, if it's not determined by the geometry of the ends of the manifold, or if
yes, yes, of course, because it's but what aspects of the geometry of the ends of the manifolds? That's the main question that we're trying to ask.
So you could have
right?
have positive curvature, lots of positive curvature in a compact set, for example. To have
yes.
this. Okay.
Yes, and you can change the metric on a compact set and create discrete eigenvalues, right, without affecting the essential spectrum. Okay, that's why we're kind of like ignoring the compact subsets of the manifold to study the essential spectrum. But of course, here you can say, okay, to any of these, you can always change, yes, a compact subset, and you're still going to get the same result. That's why this theorem that I wrote here talks about the behavior of the Ricci curvature at infinity, essentially. Did that answer your question?
Yes, thank you.
Okay, you're welcome. Anything else before I move on? Just trying to make the argument for the generalized Weyl criterion. Let me just say that if one usually tries to use the classical Weyl criterion, in other words, trying to find the sequence such that delta minus lambda at the approximate eigenfunction goes to 0 in L2, is very restrictive because there aren't many canonical eigenfunctions or forms that one can use on the manifold that behave nicely once we apply the Laplacian to them. The nicest ones are usually functions of R, of the distance to a fixed point on a general manifold. And unfortunately, the Laplacian of R, as we all know, has a very bad singularity on the cut locus. And this bad singularity is not L2 integrable, but it's L1 integrable. So it's nicer if we can find something in L1 that can be used to give us information about the spectrum. Using the classical Weyl criterion, so therefore it was very difficult to find a general theorem like the previous one. And different approach that many people have used in the past use an LP independent result for the spectrum of the Laplacian. In other words, if we know that the spectrum of the Laplacian is the same for all LP spaces, we just term proof this is true on manifolds that have Ricci curvature bounded below and uniformly sub-exponential volume growth, then one can compute instead the L1 spectrum, show that that is 0 to infinity, and conclude that the L2 spectrum, which is harder to find, is also 0 to infinity. And this was done by Wang and also by Lu and Zhu earlier on. Okay, and the manifolds over which they achieved to show this were manifolds with asymptotically non-negative Ricci curvature and uniformly sub-exponential volume growth.
Nelia, could you say in a few words what is the LP spectrum when P is not 2?
The LP spectrum when P is not 2, what could it be?
I mean, what is the definition? What does it mean?
Okay, so you have to generalize the Laplacian. So you have, okay, so for the Laplacian, you start for the Laplacian on these compactly supported C0 infinity functions or forms. You extend it and you close it in L2. Then you can talk about its heat operator on L2. Easily extend the heat operator on LP whenever the curvature tensor on K forms is bounded below. Okay, it's an analytic result to prove that. It's not very difficult to prove. So then you can say, okay, the Laplacian on LP will be the generator of this semigroup. Okay, so you do it through the heat operator to define it on LP. That's the standard.
Thank you.
Okay, anything else? Okay, and let me note that because L infinity is this weird space, L infinity is the dual of L1 always. Okay, so you define it on L1, and for L infinity, you look at the dual. So let's see, promise you to talk about form. So let's look a little bit into this maximal form spectrum. Is it a reasonable question to ask? Can we find a large set of manifolds over which the spectrum of the Laplacian on K forms is now maximal? And trying to work this problem through, one realizes very quickly that very strong assumptions have to be made on the decay of the curvature and the structure of the manifold, because now you have to build these K forms, right, that behave nicely under the Laplacian, and now you're talking about third order derivatives of R, and things get very complicated very, very quickly. Okay. So sort of a midway result, that an initial result that we found with Zichin when we started considering this problem was to prove, first of all, that if we have now a positive number in the L2, now I'm talking about L2 spectrum in the first half of the talk, okay? So forget about LP for now. So we have a positive number in the essential spectrum of the Laplacian on K forms. Then this number must belong either to the essential spectrum of the Laplacian on K-1 forms, or on in the essential spectrum of the Laplacian on K+1 forms. So it must have come from one of two places. Okay? And this has to do a little bit with the Hodge decomposition theorem for K forms, for L2, for the space of L2 K forms. But to prove these results for non-compact manifolds, we had to use the generalized Weyl criterion, because we weren't able, Dodds-Hughes result for the compact case is not as easily generalized. However, this result immediately tells us that if we're looking at the one-form spectrum, then this set, if we take away 0, it's always going to contain the function spectrum. So the one-form spectrum is always larger than the function spectrum. And whenever, so therefore, whenever the function spectrum is maximal, then the one-form spectrum will also be maximal. In particular, in the case that we saw before, of Ricci curvature asymptotically non-negative, and the volume not decaying exponentially. However, it turns out that the form spectrum doesn't have to be maximal even on a completely flat non-compact manifold. I'm going to give you a nice example that was pointed to us by John Lott. We take the 4-dimensional product space of R by the 3-dimensional compact flat manifold now that was constructed by Hanse and Wendt. This 3-dimensional flat manifold is nice in the sense that it has a vanishing first and second Betti number. In other words, it doesn't have any harmonic 1 forms and doesn't have any harmonic 2 forms. So what we can show is that over this product space now, the spectrum and the essential spectrum of the Laplacian on functions and 1 forms is 0 to infinity. Okay. I missed the delta from the second sigma there. However, the essential spectrum of the Laplacian on 2 forms and the spectrum, all of the spectrum, is now an interval that starts at a positive number. And this positive number is the first eigenvalue of the Laplacian on 1 forms over B, okay, which is the same as the eigenvalue of the Laplacian on 2 forms because of Poincaré duality. At the same time, if we take the warp product of R by this 3 manifold, and our warping function decays like 1 over R away from at infinity, away from a center, asymptotically 0, in other words, in this sense, we can prove that the essential spectrum of the Laplacian on 2 forms is empty. Okay, so we study the operator on 2 forms and prove that find an equivalence operator that's like a Schrodinger operator and show that the potential of this operator goes to infinity. And in other words, the spectrum will have to be discrete in this case. So the essential spectrum will be empty. In other words, we see that the form spectrum is more complex. Even in the flat case, the bottom of the spectrum can be positive. And it reflects these more complex substructures of the manifold that are not read by the function spectrum. Okay, so we have flat manifolds where the spectrum is not maximal, and we can have asymptotically flat manifolds whose form spectrum is even empty.
Nelia, can I ask?
Yes, of course.
Are there examples where the spectrum on function is not maximal, but the one spectrum is maximal?
I haven't been able to find. No.
Okay.
No, but yeah, I would have to look a little bit harder for that, I think.
Thank you.
Yes, it's an interesting question. A non-compact flat manifold. So the first thing that we, okay, let's try and compute the form spectrum on flat manifolds to begin with. So these are quotients of Euclidean space by a subset of the Euclidean group. These are not necessarily product because we have some weird glide rotations that don't let them break into a product of Euclidean space times a flat compact manifold. However, using the properties of the Euclidean isometry group, we can prove that the spectrum of any flat manifold coincides with the spectrum and the essential spectrum of such a product space of some smaller dimensional Euclidean space times a compact manifold. I'm calling it here B. And this B is a quotient of R of Euclidean space by a subgroup of gamma. Okay, the original group gamma essentially reflects the structure of the manifold at infinity. So we avoid all subgroups of gamma that just describe how things are going on in small scale and look at really what happens at infinity. So, given this fact, now we are reducing the spectrum of a flat manifold to the spectrum of a product manifold of Euclidean space times a compact flat manifold. And as in our previous example, we can show that this spectrum will always be an interval. Okay, and there will be no discrete isolated eigenvalues. this bottom of the spectrum, let me tell you, okay, we have Poincaré duality. So for K forms and N minus K forms, it's the same value. And it's determined by what the product is. If the order of the forms is smaller than the dimension of the Euclidean space, the bottom will be 0. But if we have to resort to forms from B, it's also going to reflect the eigenvalues of B that we have to use. And we can choose, of course, always the smallest one. You can read this formula at your ease with more detail later. So like I said, for the function spectrum, we know it's maximal when the manifold is flat or asymptotically flat in some relatively general sense. But for the form spectrum, we can't expect it to be maximal even in the flat case. And we've seen an example in the asymptotically flat case where the two-form spectrum is even empty. On the other hand, in negative curvature, we can expect an arbitrary number of gaps in the essential spectrum. So a reasonable question to ask is, okay, what are now manifolds over which the essential spectrum on forms is a connected interval? So what we did was we considered what we thought would be a reasonable candidate. In other words, manifolds with curvature asymptotically 0. And our result was about the case of an asymptotically flat manifold in the sense that the curvature tensor vanishes at infinity. So not asymptotically flat in the sense of general relativity where you assume that it's also Euclidean at infinity. No, we don't assume that. We just assume that the tensor goes to 0. So what we showed was that over these asymptotically flat manifolds, the essential spectrum on K forms will either be an interval or it will be empty. I want to give you a few words about our proof and how it goes. The main argument, as everybody pointed out, is that okay, the essential spectrum depends on the ends of the manifolds. And moreover, we can show that the bottom of the spectrum is captured by a sequence of very large geodesic balls. And moreover, when the manifold has Ricci curvature asymptotically more negative, we can choose the size of these very large balls. Let me be a little bit more specific. So what we showed, okay, I'm talking about asymptotically flat, but this first lemma holds in a little bit of a more general case, where if we have a manifold with Ricci curvature asymptotically non-negative at infinity, and I choose any sequence of radii going to infinity, then I can find the sequence of disjoint geodesic balls whose centers go off to infinity. Ricci curvature is asymptotically non-negative on them, right? And if I look at the first Dirichlet eigenvalue of these large geodesic balls and take its limit, it's going to take me to the bottom of the essential spectrum. Okay, and I'm talking about K forms now. So I'm going to call this sequence a minimal sequence because it's going to take me to the bottom of my spectrum, of my essential spectrum. In addition, over manifolds with Ricci curvature asymptotically non-negative, not only we can choose the radii of this sequence, but we can always replace this minimal sequence by another minimal one contained in the original one. So we can also replace it. So we have some flexibility in choosing this minimal sequence. So what we did is describe the behavior of the essential spectrum. We have another property. We showed that we can describe it with respect to Gromov-Hausdorff convergence, with respect to the following Gromov-Hausdorff approximation type of result. So we start out with a sequence of disjoint geodesic balls, like our minimal sequence. And we assume that we have a sequence of compact manifolds that have uniformly bounded diameter, such that we can get approximation maps from our geodesic balls to the products of these manifolds times some Euclidean space. So we have a product of some Ni times Rm. And these approximations are close in the Gromov-Hausdorff sense, in the sense that if we pull back the metric from the product space onto the geodesic ball, then these metrics are 0. They approach to 0 as I goes to infinity. Okay. And moreover, we assume that these maps are diffeomorphisms onto their image. So when I pull back the metric of GI, I mean from the image, right? So I'm not necessarily saying that I have an approximation from a geodesic ball to the full product manifold, but rather on a ball in this product space.
Excuse me,
Yes.
what is the norm in this definition on the tensors?
It's the, okay, so you have the pullback of two metrics, right? So you can look at, you can define now on these pairs of x vectors on your tangent space. These are closed, right? In this sense.
But is it in L2 space? Like an
No, it's
or
just
like a
absolute
straight line
value.
or-
It's an absolute value.
Okay,
This
thank
is
you.
the metric. This is just the
okay.
closeness of the metric in the Gromov-Hausdorff sense.
Okay,
Nothing
you.
more than that. Okay. So no L2, just the metrics are closed. So what we can show now is that if we have this closeness of our geodesic balls to these product manifolds, then the essential spectrum of the Laplacian on M is going to contain an interval, and this interval will start at the limit of the bottom of the spectrum of the product manifold. So these are product manifolds. Of course, the spectrum of the Laplacian on K forms, like we said, it can be proved it's an interval. It starts at a number, calling this number lambda 0. Okay, I look at the limit of this lambda 0. What we showed is that if our metrics converge, if our spaces converge in this Gromov-Hausdorff sense, then the limit of this first eigenvalue will be the bottom of the spectrum of the Laplacian on M. And if the sequence I chose is a minimal one, then this will be the full spectrum, okay? Essential spectrum. There will be nothing more than that. So to prove this result, what we did essentially was to show that the pullbacks via the approximation maps of approximate eigenforms in these nearby spaces, in these nearby product spaces, they give us nice enough test forms to satisfy the generalized Weyl criterion on M. And we couldn't, they are not nice enough to satisfy the classical Weyl criterion, but they are nice enough to satisfy this more generalized version of the Weyl criterion. Okay, so let me quickly tell you what this generalized version of the Weyl criterion is, since I've talked about it so many times. It works in general on any densely defined and self-adjoint non-negative operator on a Hilbert space. And we can say that a non-negative real number will be in the spectrum if we can find a sequence of test functions with uniform norm 1, here would be L2, and such that the pairing now of two powers of the resolvent operator of H paired with H minus lambda on this test function tends to 0 along our sequence. And if we can find test functions that go to 0 weakly in the Hilbert space or in L2, then the point will be in the essential spectrum. So the proof is an analytic one, uses a spectral decomposition theorem to rewrite our assumptions. And the nice part about this result is that the resolvent operator now is always an operator which is bounded on L infinity. So if we have these nice bounded test functions or forms, all we have to do is show that somehow the L1 norm of H minus lambda psi j goes to 0 as j goes to infinity. So this is the key factor that reduces the regularity and smoothness of the test functions and forms. And it was inspired by the work on quadratic forms due to David Krejcik. So this generalized criterion, like I said, is an important one because it allowed us to reduce the regularity estimates for these approximate test functions. And what we are able to show in a sense is that if our metrics are close in the Gromov-Hausdorff sense, then the spectra are also of the two spaces are also going to be close. And the intermediate step to getting that is proving that the half Laplacian operator d star d these operators are close between one space and the other, and also the resolvent operators of these Laplacians are close whenever these Laplacians are close. Okay, so and then use our generalized Weyl criterion where the resolvent operator approaches to prove that the spectra are also close. Moreover, like I said, if the sequence we choose is minimal, we capture the full spectrum of the original manifold. So a similar technique had allowed us to also show that we have a continuous variation in the spectrum whenever the metric of the manifold varies continuously, again using this generalized Weyl criterion and extending the compact case that was done by Dotzuk in '82 to the non-compact case. However, the difficult part in proving theorem 3 was actually showing that we can approximate our minimal sequence with these very nice product spaces. And the way we did that was by extending certain results of Cheeger-Fukaya-Gromov to describe how these minimal sequences, the minimal sequence behaves under Gromov-Hausdorff convergence. And the important part in this convergence theory is that the sequence will not only converge pointwise, but the metrics will also converge, and therefore they will give us also information. It will also give us information about the spectrum of the manifold. So note, first of all, that there could be varying types of minimal sequences on a manifold, but they will all lead to the same value for the bottom of the spectrum. For the proof, we're going to start out with a minimal sequence and take the pointed Gromov-Hausdorff limit of these balls with their center. And we know that a subsequence of these balls must converge to a metric space. And we have two cases depending on the injectivity radius at the center. The first case, and the simpler one, is the one where this injectivity radius remains bounded below by a positive constant. This is the non-collapsing case. And this is a little bit easier to study because we know that the limit space will now be a smooth manifold with a C1 alpha metric on it, and it will also be flat. So for this one, we can use Fukaya-Gromov's result to have these nice epsilon approximation maps that are diffeomorphisms onto the images. And as in the approximation theorem that I wrote before, theorem 5, we pull back the approximate eigenforms from the limit to the original manifold to construct approximate eigenforms on it and prove that everything in this nice interval will be in the spectrum. So the bottom of the spectrum will now actually be, our spectrum will coincide with the spectrum of the flat product limit. Note that in the case that the injectivity radius tends to infinity, our limit space will be Euclidean space, flat, and the essential spectrum of the Laplacian on K forms will be maximal for all K. The most difficult case is the collapsing case. In general, here the limit is going to be just a metric space and it can be singular. So what we did to study it more carefully was go one step further and consider what's known as the orthonormal frame bundle over M and take a shrunk sequence of it. In other words, a blowdown of this orthonormal frame bundle. The factor that we choose to blow down is so that the curvature tensor still vanishes at infinity as our balls get larger and larger, but the radius of the balls at the same time goes off to infinity. Stays large. And what we show is that, okay, we have a minimal sequence that can collapse to a non-smooth space. And the worst part is if this center, because we're taking a pointed sequence, the center is where the singularity happens. And what we show is that we can always replace this minimal sequence, but by another minimal one that's going to be centered at the regular part of the limit space. okay, and it will be minimal, but now it will be converging to a smooth limit. So we show this by carefully describing the structure of the limit space and considering the Laplacian on these two. So our proof strongly relies on the fact that the curvature tensor vanishes on the minimal sequence so that we can take this blow down, because otherwise, if curvature is just bounded below, it's going to blow up. So now that we have convergence to a nice smooth space, we can get local approximation maps that preserve the metric perpendicular to the fiber. And we can prove that our minimal sequence will be close to these product manifolds of Euclidean space times an almost flat manifold Ni in the Gromov-Hausdorff sense. And our proof uses the work of Fukaya for the behavior of the orthonormal frame bundle to be able to better describe how the metric breaks down on these two spaces. So from our theorem 5, the convergence of the spectrum result, we get that the spectrum of the original manifold will be empty, and if it's not empty, it will be an interval that reflects the first eigenvalue of the fibers. Questions so far before I move on?
Can you say a word about the role of the bundle here, the frame bundle?
So the frame bundle allows us to break the part that's going to stay a little bit flat, sort of like a Euclidean space. And we show that the fiber is better described by this, the quotient on the frame bundle. That's the part of the orthonormal frame bundle. That's the part that's going to collapse at the end of the day. And the orthonormal frame bundle allows us to recover this thing that will be collapsing and to better describe it. So it's not as easy to do if you just look at M on its own, but if you move up to the orthonormal frame bundle, you can keep the structure of the fiber that's going to collapse at the end of the day without losing it. So in the case of Ricci curvature asymptotically non-negative, one can also look at the behavior of the spectrum under this Gromov-Hausdorff convergence. The problem with only assuming a lower bound on Ricci curvature is that now the limit of this pointed sequence will be significantly more singular. Okay, so it's more difficult to control to describe the limit space under this weaker assumption. However, using some of the results of Cheeger and Colding, we are able to show that if we have a manifold now, with just a sequence of disjoint balls on which the Ricci curvature is asymptotically non-negative. So in other words, we can have even ends of negative curvature where curvature goes to -infinity if we want. So long as we have this nice sequence, at least on some end, where Ricci curvature is asymptotically non-negative, then we can find the positive number so that the spectrum and the essential spectrum of the Laplacian on K forms is maximal for all K smaller than this positive number Q. This positive number Q is what's known as the dimension at infinity of the manifold or of this sequence of balls as we describe it. Note that it's always positive, so it's consistent with our previous result that told us that the 1/4 spectrum is always larger. So given that it's greater than 0, the 1/4 spectrum and the function spectrum will always be maximal. And a way to look at this Q in a simple example is that if the manifold has Ricci curvature asymptotically non-negative and polynomial volume growth, then of degree S, then this Q is at least S. So it sort of like reflects the order of polynomial growth of the manifold ad infinity in this particular case. So for the proof, what we did was use these harmonic maps that are so-called epsilon approximation maps constructed by Cheeger and Colding. And they prove some nice L1 estimates for them, which are sufficient to use in the in our generalized Weyl criterion, but not in the classical one, and we use these harmonic maps to construct approximate K forms. And if we have essentially Q of them, as they show, we can get up to Q forms with them. I'm going to end with negatively curved manifolds. I'm only going to take 5 minutes. I already gave you an introduction of what the Laplacian on LP is for P other than 2. As I said, is the generator of the extension of our semigroup to LP, which can happen whenever the curvature tensor on forms is bounded below. And note that now that we're talking about LP, we have duality for the spectrum between K and N minus K forms, but we also have duality in P. The spectrum on LP is the same as the spectrum on LQ whenever P and Q are dual LP dimensions, okay, Banach space dimensions. Moreover, since our operator is no longer self-adjoint, then its spectrum can in general contain non-real eigenvalues. In fact, it was proved that classical example that on hyperbolic space of dimension n+1 now, just to be consistent with everybody's notation, the spectrum on LP for the Laplacian on functions, okay, so the 0 there is for functions, is to the right of this parabola that I wrote there in the complex plane. So it's a parabolic region, which if you write down what it is, it's going to reduce to the known interval when P is equal to 2. And it's a parabola that starts at 0, 0 when P is equal to 1. At the same time, they also showed that for Kleinian groups, in other words, quotients of hyperbolic space by a geometrically finite group of isometries, the LP spectrum will also contain the same parabolic region, but also a finite number of isolated eigenvalues outside it. It's also possible to prove under fairly general assumptions that the LP, that the spectrum of the Laplacian is independent of P. We have such results both for the Laplacian and for Schrödinger operators under conditions on the curvature of the manifold. For example, as I said, Sturm showed that it's true we have LP independence if Ricci curvature is bounded below and we have uniformly sub-exponential volume growth. For Schrödinger operators on Euclidean space, it was proved depending on the decay properties of the potential, which allow us to prove essentially some Gaussian type of bounds on the heat kernel. So Gaussian type of bounds on the heat kernel let you prove LP independence of the spectrum if you also have uniformly sub-exponential volume growth, at least on a non-compact manifold. So for example, on K forms, one can get LP independence if in addition to Sturm's result, the Weissenbach tensor is bounded below. And for the square Dirac and Dirac operator, we also get LP independence if we have the Clifford contraction bounded below, and the manifold has certain symmetries that allow us to get information about the Dirac operator from the square Dirac operator. So what we recently were able to do was to compute precisely the LP spectrum of the Laplacian on K forms over n+1 dimensional hyperbolic space. We showed that it's again a parabolic region to the right of the parabola that I wrote there that now depends on the dimension on P for the LP space and on the order K of the forms. And again, in this half dimension when n is odd, it will also contain 0 for all P. The parabola I wrote here is for K smaller than half dimension and for P from 1 to 2. For everything else, you get it by duality. Note also for a fixed P, the region increases in K up to half dimension. And this parabolic region reduces to the interval that Donnelly had computed in the case of P is equal to 2. The proof of this result relies on constructing approximate eigenforms to prove that the parabola is contained in the spectrum. And for the other containment, one essentially proves that the resolvent operator is a bounded operator for every point that's not inside the parabolic region. And you do that using the wave kernel method and essentially heat kernel estimates for the heat semi. The half dimension, we had to treat this a little bit separately because we have a gap at 0. So we can't really rely on just the resolvent operator because now we have this singularity where everything fails. But here we were able to show using estimates on the heat kernel that even for the LP spectrum now, the LP spectrum on K forms, again, other than 0, comes from either the LP spectrum on K-1 forms or on K+1 forms. And we use the observation that the parabola for this half dimension, if you just look at the equation that you have, is the same for half dimension, and it's the same for the K-1 before it and the K+1 before it, right? So other than 0, everything that you can have in the half dimension parabola came out from the dimension before and above, which are the same. So you can not get anything more for half dimension other than except for 0. So the only additional point is 0, and we prove that 0 is the LP spectrum in this half dimension. Take one more minute, give you some open problems. So some interesting problems that one can sort of like try and take, these are find precisely the necessary conditions so that the essential spectrum on the manifold is a connected interval. We gave a very large set here, but maybe we can do better than this. And at the same time, what are precisely the geometric and topological properties of a manifold that determine the bottom of the spectrum of the Laplacian on forms? There was some recent and very nice progress done on this problem by Boulanger and Courtois in this past year for the case of the Laplacian on 1 forms, using a generalized Cheeger constant, in other words, a generalized isoperimetric inequality that would work for 1 forms. But the problem is still mostly open in higher dimensions, in higher orders of. At the same time, there are further subsets of the spectrum that one could consider by looking at the spectral measure of the operator. These can be classified into further subcategories like the absolutely continuous spectrum, the singularly continuous one, and the pure point spectrum. These are all subcategories that are less rigid under perturbations of the metric. And it would be interesting to see what type of perturbations or properties on the manifold preserve them or to prove vanishing and existence result for it, depending on the geometry of the manifold. There was some work done for the case of the Laplacian on forms by Donnelly, but probably there's still a lot of things that can be answered in that direction. So I really want to thank you for your attention, and I'm open for any questions that you might have.
Thank you very much for this nice talk. And as you mentioned, there is time for questions. So if you have questions, please either unmute yourself and go ahead, or ask them in the chat.
Okay, so
there is a question already in the chat where it is asked, apropos of the injectivity radius, can we know almost explicitly if upper, respectively lower bounds for a non-compact hyperbolic manifold?
This was asked just now, right? So you mean if we look at the a sequence of manifolds, non-compact hyperbolic manifolds, collapsing sequence, and we're talking about the injectivity radius like that, or
so
a non-compact hyperbolic manifold has injectivity radius uniformly bounded below, right? Around the collapse would happen if we have a sequence.
So, okay, I'm not sure if this answers.
Oh, so if we have a sequence of manifolds with Ricci curvature simply bounded below, yes, it can collapse and it can be very bad. If they're just hyperbolic, I mean, we have a discrete group, so it would have to be somehow a limit. You would have to look at the limit of the quotient group And depending on where the quotient group converges, that can be the limit of, so your limit will be the quotient of hyperbolic space modulo the limit of gamma, of the groups gamma I, right? So that can be, I think, very bad. Okay.
Any other questions? So I have a very naive one myself. Your results in the beginning were for asymptotically flat, or even with you had a condition on Ricci for the limit. Are there anything known for if you have only scalar curvature conditions in the, or does my question make sense?
No, it would, I mean, we haven't worked. Well, okay, so our asymptotically flat is the full curvature tensor. So I mean, scalar curvature would also go to 0, and Ricci curvature will also go to 0. If you only assume scalar curvature asymptotically non-negative, sort of like a lower bound that goes to 0, then I think even less is known than for Ricci curvature, right?
Yeah.
Maybe if you assume sectional curvature going to 0, maybe you can do something.
In the beginning of your talk, you had results, perhaps older results where the condition was on some Ricci in some direction, no?
So you only need to assume Ricci in one direction for the function spectrum. It's enough.
Okay.
Right? You don't have to assume Ricci in every direction, just in this radial direction away from a point. So that's weaker than assuming Ricci going to 0 asymptotically from below.
And in this context, scalar is not enough.
From what I know, it's probably not enough. Yeah, I mean, you would have, maybe you can think of, say, a product of some compact negative space form, curvature -1, times some sphere, curvature 1. Like you add the 2, you get 0, and then the spectrum is.
Thank you.
You do times R, then you find the minimum, and then whatever, you get something weird, right?
Does anyone else wants to ask something or comment on something?
Yeah, I was wondering, in, I think, the first theorem, you were saying that there's no discrete spectrum and that the essential spectrum is the same as the whole thing.
For the flat manifolds, yes.
Yeah. Can you say something about embedded eigenvalues? Does it say something about
the embedded? So I think, okay, there are no L2 eigenvalues on a flat manifold or eigenforms. So that
like,
we know.
Never ever.
Never ever.
Okay.
Never on a flat non-compact.
Okay, so anyone else wants to ask something? Not, let's thank our speaker again. Thank you very much.
Thank you all for coming here and listening.